So today we're going to continue with distributions. So far we've talked about the normal distribution, right? So we've characterized the population, we've compared the sample to a normal population and the distribution of a normal distribution. So we've compared sample means to population means. What was a very unique feature now of the so-called STAT test or STAT statistic was that the variability of the population was given. And this was given in all the questions and all the examples you basically had to solve so far. So that means that you know the variability in a population. You're using this variability of the population to estimate the variability for hypothesis testing, of course, to estimate the variability of your sample means. So you estimate the distribution of the sample means. So for obvious reasons, this is important to compare your sample mean to the population mean. So now in a setting where you do not have the standard deviation at your disposition, you can estimate the standard deviation of your population using this estimate to estimate the variability of your sample means. So you're estimating now the standard deviation of your population, which you cannot measure, right? It's like if you had every single cholesterol value of an US adult, this would be a perfect world scenario. You cannot measure everybody, so you need to estimate it. And for this very reason, we're going to talk today about the so-called T-distribution. The T-distribution is a way how you can estimate the standard deviation. And this was actually, and this is, well, it's not anecdotal, it's actually historic fact. So the reason why this distribution was actually invented was by a gentleman who actually was not a statistician nor a mathematician. He was the chief brewer of the Guinness brewery in the UK. And so the problem at hand was that beer needs to have a certain quality criterion before it's being sold, or before it's being closed, bottled, and sold to the customer. So they had a problem. They had a large output of beer, of bottles of beer, and they were not able to estimate the variability of this quality criterion. So I'm not a beer expert. Well, whatever the reason, but so essentially you have a certain variability of this quality criterion in your entire population, and they meant to estimate this variability of the entire output of beer on a day, which they couldn't all measure, by using small samples. And they actually found that when they have a small sample, they have a variability of that small sample, of that quality criterion. I don't know what essentially it was, alcohol, or I don't know what other purity measures they have. They were able to estimate the variability of an entire day of that quality criterion. Yes?
I know we kept on saying before this, that you have a sample, like it can't be like that. It's not really representational of population. So it's like a new tool to be able to do that?
Well, the mean of the population, right? So you're trying to now find a means to estimate what is the variability of the population to essentially inform the estimation of the variability in the sample and the variability of those mean estimates of each individual sample that you have drawn. And that's now the idea, because your sample mean, your estimate of each sample, you draw 100 samples, you will have a variation of these mean estimates that all mean to estimate the true mean, which hypothetically in a perfect world would represent the population mean. So when the variability in your population is larger, that variability of those sample means is also going to be larger, because you're more likely to take extremes, and that's how you introduce more variability in the estimate of your sample means, or your sample estimates. So now you essentially, and this is related by the central limit theorem, by standard deviation of the population divided by square root of the n, and we have discussed this ad nauseatum. So now basically, now you're trying to estimate the variability of your population by using the variability within your sample. And this also is now the reason why I was so trying to be so diligent in pointing out you used STDEF.S, or used the standard deviation formula in Excel, and not the STDEF.P, which I asked you to do, because STDEF.P is that estimate of the standard deviation using the population formula. Now there's a sample formula which you utilize to estimate that population variation.
The variability in the sample to
Estimate
show us the variability in the
population, exactly. That is the idea. And this is the t-distribution. And the underlying principle here is that when you have, and this is now the magenta, turquoise, the turquoise distribution here, let's assume this to be a normal distribution, the variability of a population. So now you have in the t-distribution, you have here 3 different examples of different sample sizes. So you have here the t-distribution of 2 individuals, the t-distribution of 8 individuals, and the t-distribution of 30 individuals. So the larger the sample size, the more likely your distribution will start to resemble that of a normal distribution. Yes.
How come the formula is running? Isn't standard deviation the formula the same no matter what? So why can't you do STDEF.P? What's the difference?
Well, we'll get to the arithmetic part of it. So what is different? You are now not okay. Let's not. So it's slightly different, and there's a modification factor in the calculation of the variance that basically changes your estimate of that variance, of the variability, that essentially leads then to the standard deviation.
When you're using the sample method.
When you use the sample standard deviation formula. And this is with the aim to essentially estimate what the normal distribution looks like and what the standard deviation of the normal distribution looks like. So that's kind of the basic idea. So you try to modulate that formula to get closer to an estimate of the standard deviation in the population, and even with small sample sizes, under the assumption that you only have a small sample of that population and you can't estimate the standard deviation from the whole population. For you to know when to use this, and this is the distinction which I need to emphasize, and please memorize that for the final, because that's one of these problems you will be facing at the final, is like, which method am I going to be using? Am I using a standard deviation? Am I using a STAT statistic, or am I using a t-statistic? Look at the standard, whether the standard deviation is given, and look what the sample size is, because the sample size will inform these critical values.
Explain that, like if the standard deviation is given, then what does that mean?
So the standard deviation, if you have a question where where it says the standard deviation of the population is XYZ, then the standard deviation is given to you. And if it's explicitly said it's the standard deviation of the population,
that means that we're
using
focusing, that we're STDEF.P.
exactly, and the SET test, the SET statistic. If you have a sample size less than 30, and you have a standard deviation of your sample, then you're using a t-distribution. And that is
less than 30 average.
Less than 30, and the standard deviation is either from the sample, given from the sample, or you have to calculate it yourself, which can also happen to you moving forward in the questions. So that will prompt you to essentially use the t-distribution and the t-statistic that we'll do today. The rest is rather simple. So it's not going to be, we're not reinventing the wheel. It's basically, it's a very comparable dynamic, but there's some entry differences that will essentially be important for you to recognize. Then the t-distribution is a stroll in the park. Yes.
So if the sample distribution is less than 30, then you can't use the STDEF.P or the t-statistic because it doesn't resemble the normal curve.
Correct. So that's why you're trying to manipulate it with that formula we will be discussing today, which is not marginal, it's marginally different, but it's conceptually quite importantly different. And this is where you try to essentially, in the end of the day, what you try to expand the variability estimate by a constant manipulation that allows you to get a more realistic estimate of the variability. So you blow up your estimate of the variability. Because if you have 2 participants like how much estimates can you really make based on 2 participants, right? So you basically you try to have 2 to estimate this. So when the sample size increases, the standard deviation approaches sigma. Again, statistic, parameter, statistic of a sample, parameter of a population. So standard deviation will approximate, will get closer, approaches the sigma and the population parameter, and T and set become equal. What that means, I will tell you in a second, because we're moving away now from using the set for the standardization of the normal distribution. We're using now the T. And we will get to that, what that means.
The T is like different, but the same type of thing as Z.
It's actually not different. It's conceptually different because it's derived differently, but the interpretation and all what we did afterwards is going to be exactly the same. So hypothesis testing per se does not change.
Same table.
Nope. And that's the next issue. But we'll get to that.
What is test surface there?
Standard deviation.
So standard deviation of the sample, for example, standard deviation of
So the standard deviation of the sample approaches the sigma, which is the standard deviation of the population. So also as a rule of thumb, and this is what 30 is indicated here, as soon as your sample has a sample size of 30, you get away with using set statistic. Everything less than 30, you are meant or you are asked to use the T distribution. In essence, we will look at that later. It's actually not very accurate to do that, but that's a different conversation. But generally, the consensus among statisticians is that when you have a sample size greater than 30, you get away with the normal distribution of the set statistic. So the calculation. So we remember the population standard deviation. So that's this. You calculate for each individual entry the deviation. So that's X, the individual score, minus the mean, the sample mean, notably. You square this deviation, you get squared deviations, as many as you have sample size. You sum that up, and you are at this super important parameter of the sum of squares. The sum of squares divided by the sample size, n, gets you to the variance. The square root of the variance gets you to the standard deviation. We've done that, right? That's simple. So now we're introducing a new concept. The difference is marginal, right? Conceptually, it's the word, because you mean to extend the estimate of that variability. And you're doing that by introducing a new parameter, which is n-1. Now that sounds super easy, and it is super easy. It's just important in principle to keep in mind what it means. It's from now on, n-1 will be called the degrees of freedom. And the degrees of freedom are actually those entries in a data series which you use for the estimation of the standard deviation that are freely variable. But what really needs to add up is that last parameter in your data series that leads you to the estimation of the sum of squares. So when you mean to characterize the association between the sum of squares, which are here on top, and your sample size and that variability, there's one parameter in there, knowing the sum of squares, knowing all the other parameters, but there's one parameter that you actually don't need. You drop that one because it's a resultant of that association between the sum of squares and all your other data points. That's the definition of it. It's pretty much like approaching a traffic light and saying like, okay, so it's red, I can't drive. And your co-driver tells you when to drive. So it tells you, no, don't drive, it's red. And then you basically still stand and it's yellow, and your co-driver, no, don't drive, it's yellow. But then the last resultant is where your co-driver tells you drive, because you don't need to know what color it is anymore, because the only resultant outcome is essentially drive, because it needs to be green then. That's the example that is given. It's somewhat understandable because the sum of squares, that variability is given from the population, but your data set essentially can vary by this one redundant entry. Anyone. but one can drop because you know the variability that you're aiming to represent.
How do you choose like which one?
You don't have to choose it. You just assume to not take the sample size anymore in this estimation, but you use the degrees of freedom. And these degrees of freedom will repeatedly come up because they are basically which drive all this distribution that we will be using moving forward. So that involves the F statistic for ANOVA, involves the chi-squared distribution. So all this distribution we will be discussing moving forward will utilize degrees of freedom for characterization. Yes.
So do you only use this equation when your sample is less than 30?
Yeah, hypothetically. In practice, you don't. In practice, you use it pretty much for all standard deviation calculations. But in principle, you essentially could utilize the other equation for samples greater than 30, hypothetically. But you will see why this is accurate, and it's basically more appropriate to use this distribution even with larger samples.
And also, is n minus 1, is that the sample size minus 1?
Exactly. So if you have a sample size of 30, your degrees of freedom is 29.
So if you're just dividing by a slightly smaller number, the answer is only going to be slightly bigger.
Exactly. And that's why you do it, because you want to blow up your estimate of the variability. And this is why they needed to find a way. And that's why the concept of degrees of freedom was involved, because you mean to kind of expand the estimate of your variability with the aim to make it a more realistic or more accurate estimate of the variability of the population, which they knew was larger. So that's why they introduced this concept as a reason. So now you have okay, so it's easy how to calculate it. One aspect is just important to keep in mind, and this is the formula right here. So we will do hypothesis testing now using this new distribution, and you will see an example how you could be facing it on your final or on the quizzes. What's important to keep in mind is now that when you calculate your standard error of the mean, same formula, but keep in mind it is the same formula. Regardless of what you did with the standard deviation, the formula for the calculation of the standard error of the mean is the same, and it's not n-1. Because the relationship between the estimated standard deviation of the population and your variability of the means is still the same. Even with the smaller sample size. Because you're assuming that the standard deviation that you have estimated is already the standard deviation of the population. So the standard error of the mean is then just taking the population or whatever estimate you utilize for that estimate for estimating this population standard deviation. So the standard error is the distribution of the sample means. It's the variability of these mean estimates that you have. And you basically have an estimate of the standard deviation. And the relationship between the standard deviation estimated by the sample, but representing the standard deviation of the population, and that association to the variability of your sample means is still the same as it's always been. The only thing that changes is your estimation of your standard deviation. You're just changing it because you assume when you increase your estimate of the standard deviation by decreasing the denominator by 1, you get a wider distribution, thereby something that is more closely representing a normal distribution as if you would have found it in the normal population. Okay? Kind of. Well, it's gonna get easier. Okay, standard error of the mean still divided by the n. Do not use degrees of freedom. Common mistake I've seen. So please don't. No, don't use degrees of freedom. Okay, so now we're doing an example. And that it's basically hypothesis testing in the same fashion as we've done for the STAT test. It's just good to see it once in practice. Okay, following example. So in education, in psychology, and various other aspects, in addiction counseling and a million other things, you try to empower and encourage the subject, the participant, the patient. You try to encourage and empower the individual to take leadership of their own actions. And you do that by reinforcing their wish to improve their behavior. And you do that by essentially have them sign a contract, quote unquote, sign a contract with themselves. Not only with themselves, but also with their counselor. So here the idea is, and that's example 9.6 in chapter 4. So you have a university counseling center, and they know from the entire university that students come in quite infrequently, and an average of out of 10 sessions, a mean of 4.6 sessions will be attended by students. So they took the overall population, so they know each student is supposed to come for 10 sessions, but in essence, they only come 4.6 sessions. So now they are testing the intervention of having the students sign this contract with their counselor and themselves, and they're like, I commit to come in 10 sessions. And so as said in psychology and education and addiction counseling whatsoever, this is being used to encourage participants to come more frequently. So now the intervention is to have them sign a contract. So now the idea is, are these individuals indeed coming more often? And this is now the hypothesis which we're testing. So we're hypothesizing that signing that contract will inspire them to come more often to the counseling session. So this is being done and estimated based on a sample of 5 students. I'm well aware it's not a very strong case, but on 5 students, we basically mean to now estimate the variability of that sample. Use that as the variability of the population, use that to estimate the variability of the sample means, do the hypothesis testing, do the 95% confidence interval, so go through the 6 steps of hypothesis testing. And that's essentially what that example is. So what we have now is, so we have 4.6, that's our population mean.
We have this on canvas or not?
Yes, it's on canvas, yeah.
Can I just ask a question about, I'm confused about one part of the question.
Please.
Is 4.6, is that the mean amount of sessions they attended before they had to sign a contract?
No, we're not yet. So that would be a paired fashion where you use, where you compare within individuals. This is a population mean. So when you read the question, one study reported a mean of 4.6 sessions. Let's imagine that the counseling center hoped to increase participation rates by having students sign a contract to attend at least 10 sessions. 5 students signed the contract, attended 6, 6, 12, 7, 8. The researchers are interested only in the university. So they treat the mean of 4.6 sessions as a population mean.
Oh, so 4.6 is the mean of those numbers.
Exactly, and this is what I meant was like, read the question in much detail, because half of your answer is already in there. The rest is just the methodology that you employ. And this comes back to what I said. Statistics is really not so much about the methodology, because that's super simple, right? It's like calculating the differences, standardizing it. Once you have that, it's considerably easy. You just need to know when to employ what test. And that's also the reason why I have the final cumulative, because that's the take-home message, is like, know what test to use. The arithmetics behind that is super simple, I'm well aware. So that's a story in the pot. So, but what we need to do now first, we need to estimate that variability. Simple, right? So we need to calculate a mean. Mean is calculated as average of D4 to D8. That's our average.
So what did you include in average?
D4 to D8. So just these 5 samples. So these are our acts.
This is after they signed the contract.
This is exactly, that's the observation of after they signed the contract. So this is 10 of their sessions, and did they actually, so when you look at that, that's 5 different students. They signed the contract, they would attend 10 sessions. They're only attending 6, and there's a very eager one, came 12 times, then we have 7 and 8. So that's essentially, that's our,
Mean of a sample.
that's the mean of our sample. Yes, correct. So now if we calculate now our deviations as an x minus m, this is logically D4 minus $D $10. So that's our deviation.
Can you write what you said?
Well, it's D4 minus D10. But you need to lock D10 in with the dollar sign. So now if you want to now next square this, you get the squared deviations. That's easy. So you just square each individual entry, but so you square it, gets you those squared deviations. And now next you get, by summing that up with the sum function, you get the sum of squares. So the sum of squares is 24.8. And now you're basically coming to the interesting part, because now you want to quantify the standard deviation. And we have, okay. So if you do the sum of squares divided by, so the square root, sum of squares divided by your n, which is 5, which is count of these 5 minus 1, will essentially get you to your standard deviation, right? So that's your standard deviation.
How to put it to the, you have to do minus and minus 4.
Because it's a sample. You're estimating the standard deviation. Your question does not give you the standard deviation. So that's when you automatically think of estimating the standard deviation. That's when you know you're basically resembling a t-distribution that is meant to reflect the normal distribution of the population. So now you're using n minus 1. In comparison to that, if you would use the same formula and you would do SQRT of the sum of squares divided by only the count, not subtracting the 1, you would essentially get a different standard deviation estimate logically, right? So now we expanded it by lowering the denominator by 1.
And what is expanding it do?
Well, it gives you a wider distribution. So you are getting it closer to what you would expect the standard deviation of the population to be, because in the standard in the standard deviation of the population, you include more outliers. Then arithmetically it needs to expand. That's the idea.
You said how you did the x minus m squared. What did you like to put in?
The x, you mean this?
Yeah.
That's just squaring it. So
You
that's
square each one.
each individual deviation.
You have to do each one separately.
Yeah. Or you can just put it on.
Math.
Yeah.
Why do we need 4.6?
Hmm?
Why do we need to be given the information about 4.6?
Well, because we're getting now, we want to compare now our mean of 7.8 to 4.6. So we're comparing whether the intervention was significantly different and whether it showed an improvement.
So do we have to do all this information now, but now you set 4.6 as a meaning?
Yeah, because now we're getting to the hypothesis testing, and that's what I meant with the hypothesis testing is exactly the same. Because where we're getting to now, and I want to finish the standard deviation because I just want to quickly show you, and this is the STDEF.P. And so the STDEF part is essentially if you use the STDEF function to this, you get exactly the same. But if you use STDEF.P, you get this. Now that's the trick, right? And that's why I didn't want you to use STDEF. Good. So
How do you calculate the standard deviation manually? Like the one above before you use the equation?
this one,
Yeah.
same thing. So you take the sum of squares
Okay.
and you divide it by this, the sample size minus 1 by the degrees of freedom. And that gets you to 2.49. So the idea is again, so you estimated now the standard deviation of the population. And from now on, it's the same hypothesis testing with one difference. You're using now a t-score table and not a z-score table because you estimated it basically based on a t. So this being said, the only thing we need to calculate now is the standard error of the mean, and this is again the 2.49 divided by the square root of the sample size. So that's now our standard error of the mean. So we know now the distribution of the sample means. This means basically distribute around the mean of our sample with 1.1. And now essentially we can use this formula to do the hypothesis testing under the t-distribution. So as said, the t-distribution follows the same outline as the normal distribution. The only thing that's different that the extension of the t-distribution is now changing with the sample size, as we have seen in this graph. So we see that the smaller the sample size, the narrower this distribution and the different the distribution looks. So we want to expand this to make it more closer to the normal distribution. So therefore, we're using now the t-score table, and it's on Canvas as well. So we have here rows and columns. The columns are representing now our p-values. So the p-values are now a resultant of the t-scores. So now we're using the same principle as we have done with the z-scores. We're using the same principle now with t's. We're basically calculating t-scores, and these t-scores again represent p-values that will reflect the probability of, or percentile if you use it for standardization, or probability if you utilize it for hypothesis testing. So these p-values exactly reflect again the type 1 error, and your two-tailed under two-tailed hypothesis, your alpha of 5% is in this row. So that's your 5% if you use a two-tailed test. So if you have now different degrees of freedom, you see that with each increase of degrees of freedom, your t-score, your critical values are getting smaller and smaller until they reach in infinity 1.96 from the z-score. And that's the 1.96 that we utilized for the z-score, for the hypothesis testing of the z statistic. And the reason why you get away with 30 is because the assumption is that with 30, the 2.04 are considerably close enough to the 1.96 that you kind of reasonably can utilize and draw your conclusion based on the p-value that you have concluded from your t-statistic. So 2.04 versus 1.96, it's a nonlinear function, which basically means that the gain of accuracy or precision essentially in that context that you gain by increasing the sample size further is not justifying the inaccuracies you're introducing by using the t-distribution. But for a smaller sample size, it's a very strong decrease. So you see it from 12 to 4 to 3 to 2.7. So you see a stronger decline of that critical values and that consequent confidence interval. So this being said, if we have a sample size of 5, our degrees of freedom are 4, right? So if we have a degree of freedom of 4, our critical value is 2.78. And that 2.78 is essentially just with the z-score and the z statistic. Where is it now? 14 is just like it was with the statistic. It's again demarcating on both sides, those tails where you have 2.5% probability that you are rejecting something that you shouldn't be rejecting. So that's your type 1 error. So these are again summing up to those 5% of p-value that you are willing to accept as a type 1 error. So this being said, these critical values are not only, again, and now it's 2.78, these are not only your critical values, this is also where you will be able to locate your 95% confidence intervals, which you're using now in the same fashion as you did with the STAT statistic. And this is where we're getting now in our example, because if you want to calculate now the 95% confidence interval, you're basically doing exactly the same thing as with the STAT statistic. You calculate the lower limit and the upper limit, where the lower limit is basically the mean minus your standard error of the mean multiplied with your critical value of 2.776. That is your lower limit. If you want to calculate now your upper limit, it's the mean plus your standard error of the mean multiplied by 2.776. So that's your upper limit. So when you look at these two values, you know now your critical values, you know that range within your 95% confidence, you're capturing your population mean. What's the idea now? You can conclude from that your sample showed a significant difference to your population mean of 4.6. Thereby, a reasonable conclusion could be based on the sample at hand that I've analyzed. I am looking at a significant different mean, and I look at a significant treatment effect of having a student sign a contract. So you are doing something that prompts students to come to the counseling sessions more frequently. Yes.
Why is it distinctly different means? 4.6 is right.
So the mean here is 7.8. The mean is 4.6. The lower limit of the 95% confidence interval is 4.7 and 10.9. 4.7 is greater than 4.6. So we're rejecting, we know based on the confidence interval, we know already that this is a significant difference. But we want to know this in more detail. So therefore, we're going to calculate now a t. And the t is calculated just in the same fashion as we always did. We're calculating now our test statistic. What's the formula now? So the test statistic is exactly the same as we've done in the past. It's again the mean minus our population mean divided by the standard error of the mean. So the t is simply calculated as 7.8 minus our 4.6 divided by the standard error of the mean. So we have a t of 2.87, which is larger than our critical t of 2.776. Thereby, we can conclude that we're rejecting this. So the alpha we set it at was 5%. And now we can reject the null hypothesis. Right? What the null hypothesis exactly was m equals m equals mu. And the HA is m is unequal to mu. Right? So that's exactly how you will approach this. Now you have the t, you have the confidence intervals. Lastly, with the hypothesis testing, you always want to know an effect size, right? Because the sample size is definitely breaking here the confidence with which you're going to draw this conclusion. So you want to see whether this is just a question of the variability or whether this is actually a question of the difference. So therefore, you want to calculate the effect size. And the effect size, just in the same fashion as with the STAT statistic, is again calculated as the mean of 7.8 minus the population mean of 4.6 divided by our standard deviation, which is 2.49. So our effect size is 1.28. So who remembers, is that a small, medium, or a large effect size? Cohen's D. Yes, it's large. It's a large effect size. So you have small is 0.2 to 0.5, medium is 0.5 to 0.8, large is everything greater than 0.8. Good. Any questions on any of this? I think it's simple. It follows the same outline. The only aspects that are really important to understand is how do I determine critical values? How do I read the t-score table? And how do I deal with a t rather than a set?
Can you give another example, like
Yeah.
slower though with the spreadsheet?
Yes. Oh. So let's quickly go through the slides and let's see what in addition Nolan and Heinz were saying. So also remember the 6 steps of hypothesis testing. So first characterize the population. You then estimating your variabilities. You pose your null hypothesis. You set an alpha level. You determine which test to use. You calculate your set statistic, and then you draw a conclusion based on the set statistic. So sample standard deviation calculation different to use degrees of freedom rather than the sample size. Standard error is the standard deviation, this estimated standard deviation divided by the square root of the n, not the degrees of freedom. The t is calculated as the difference between mean and mu divided by the standard error of the mean, just in the same fashion as the set statistic was calculated. You're basically calculating here standard error. You get then a t of 1.05. Some example. Yeah, that's the example. So they utilize the other example first. So this is now our t of 2.873. You determine those cutoffs based on the t distribution of the t-score table. That's probably also another key point. Make sure to have it compared against the set score table. So from the set score table, you basically start from the lowest point, so from virtually 0, but asymptotically never reaching 0. So you basically increase with an increasing value of that set. So from the lowest set on your set score table, let's actually look at this, to your mean, you're basically looking at 50%. And then from, so you come here from 0.0002 minus 3.49. You approach your 50%. And you go then in the positive sets, you go up here to almost 0.99 with 3.49. Whereas when you look at the t-score table, you are only utilizing the p-values, and these are the corresponding p-values to your t-scores and the t-scores. So now it's basically inverted, right? How you would characterize it. So you have your p-values and you have the corresponding t-score that indicates that critical value with your degrees of freedom that basically allow you to determine upon exceeding which value you basically will decrease, reject your null hypothesis. So, okay, so know how to calculate and know how to determine those critical values. So you basically have a two-tailed hypothesis. You have here the third column as being your critical value. Make sure that you don't mix up sample size versus degrees of freedom. It's just keep it in mind. So now the million-dollar question. So if you have a one-tailed hypothesis, so here it's clear, right? In a two-tailed hypothesis, you would reject your null hypothesis. If this were now a one-tailed hypothesis and you wanted to determine whether, so one-tailed, so whether null hypothesis that M is actually smaller than mu, smaller equal mu, and the HA, the alternative hypothesis, is M is greater than mu. Would you or would you not reject the null hypothesis? Based on the T that you just have calculated. Remember, in a one-tailed hypothesis, what changes is not the calculation. The calculation is going to be the same. You still calculate mean minus mu divided by the standard error of the mean. What changes are these critical values and which end of your normal distribution you're actually looking at. Remember the factors that have affected power. What are the 4 reasons that affect power? It's increasing the alpha from 5 to 10%, because that increases the tail and increases that area that is not overlapping. It's increasing your sample size because it decreases variability. And it is changing from a two-tailed hypothesis, or increasing the difference is the 4th one, but the 2nd one is basically to change from a two-tailed to a one-tailed hypothesis, because what you do is you increase in one tail what you're willing to accept. So if you are changing from a one-tailed to a two-tailed hypothesis, you're basically now one column to the left. And your critical T is only 2.13. So you essentially in the T distribution are more likely to reject the null hypothesis. So the answer to my question, whether you're still rejecting if it were a one-tailed hypothesis, is yes. You would even more so reject it because your probability of a type 1 error is now shifted on one side and you're more likely to see a difference. Okay. All right, so that was the counseling example. So now let's do another one. Okay. So this is an interesting example because in addition to that, it emphasizes how universal these applications and these equations and concepts actually are. So we have now, so you can imagine that the whole healthcare analytics bases on T distributions in small samples. In addition to that, you have now the counseling examples, which is like from education theory, then you utilize T distributions in psychology, in surveys, whatsoever. Here, for example, it comes from business analytics. Okay, so you have now employees spend 11 minutes on average on one project before being interrupted. After each interruption, they need an average of 25 minutes to get back to the original project. So maybe the reality is that multitasking actually reduces overall productivity, which we very well know. If you work intensively on one project, don't try to multitask because then you will not get finished. Suppose you were a manager of one of these firms and decided to reserve a period from 1 p.m. to 3 p.m. each afternoon during which employees could not interrupt one another, but may only be interrupted by external callers. So here's fictional data that basically you want to compare to 11 minutes as the average. So that's your mu. The 11 minutes are your mu. And these are the actual data. So that's the average that you have observed in your employees, which it takes for them to be interrupted. And then basically if you didn't allow the colleagues to interrupt the employee anymore, you basically you basically have changed that time until the individual was interrupted, which is kind of interesting because I don't know who of you are working or have been in work environments. So nowadays there's a lot going towards messaging. And you have in Microsoft Teams, for example, and you have like your colleagues being able to message you all the time, which I will not really understand how this is considered making increasing productivity, because messaging service is nice to get quick information, but it also increases the probability of the employee being interrupted, particularly for individual contributors. That's I think to some extent being counterproductive to productivity, but that's just me. Okay, I'm personally not a big fan of messaging. Okay, so now the idea is clear, right? So we have an average of 11 minutes that we have observed, and we have now 5 employees that have been studied after the. I know it's a little chilly. So we have 5 employees that basically were studied after the implementation of this non-contact period from 1 to 3. Where only external calls were allowed to be put through. So now we have here our sample, and we have our mean of 11 minutes. So we know that mu is 11, right? So that's our comparator. So now we have 5 entries. What are we going to do first? Well, let's actually start with developing a null hypothesis. What's the null hypothesis? So a null hypothesis is logically is the m equal to the mu, right? And the alternative hypothesis is m unequal mu.
What does M equal mu?
M equals mu, that's our null hypothesis. That essentially the sample that we have is identically or is the same as our initial observation, our population mean.
Meaning there's no difference.
That there's no difference, yes. You got now slowly to detach yourself from population mean or non-population mean. It's not really labeled in everything that comes now. It's not labeled as the population mean. Now it's more or less a reference value. It's some reference value that you have from a larger set of data.
How do you do this not equal to? How do you write that?
So that's me in my coding mindset. So m exclamation mark equal sign or equal sign exclamation mark indicates it's non-equal. It's not equal. It's different. Sure.
That's a better response.
Yeah, I kind of like it. So the proper way, just keep in mind the proper way should be this. Should be that equal sign that's scratched through.
Maybe we can do the
Well, I'm fine with it. Yeah. So it means kind of the same thing. It's like it means that that value does not include that other value. It comes to the same thing. Okay, so that's the null hypothesis. So now next we need to understand the distribution of this sample, which again is the actual same outline. So we have x minus m. That's our deviations. So we're having, first we need an m. So now our mean, sample mean is average of B3 to B7. So it's 12.4. So if x minus m is now x minus $B $9. So same principle, and now we calculate not that much. So now we basically have this. Now we just need to square it, and we're again at our squared deviations, which we now just have to sum up to get out to our sum of squares. The sum of squares is basically the sum of these 5 entries, which we now have to calculate. Sum of squares
Well, there's so much not.
divided to 5 is the variance, and the standard deviation. It's obviously it's 5 minus 1. That is square root of the variance. Okay, so let's walk through that. So we have individual x. We calculate the deviations. We calculate the squared deviations. We're summing the squared deviations up. We are dividing them by the count, the sample size minus 1 gets us to 4. So 35.2 divided by 4 gets us to 8.8. The square root of 8.8 gets us to the standard deviation. Here we are at the standard deviation. So once we have the standard deviation, next we want to calculate the standard error of the means. That's easy. We take the standard deviation and we're dividing it. So that's the standard deviation that estimates this population standard deviation. And now we're relating this population standard deviation to the standard error of the mean by dividing it by the square root of our sample size, which is 5, gets us to 1.33, which now can be used to calculate the confidence interval. 95% CI, LL, UL equals, so our mean of 12.4 minus the standard error of the mean multiplied by our critical value of two-sided hypothesis. We're setting the alpha again at 5%. We have a sample size of 5. We have a degree of freedom of 4. Our critical value is again 2.78. And now essentially we are utilizing this for our critical value. So it's 776 again, just like with the old example. So we have our mean minus 2.78 multiplied by the standard error of the mean gets us to the lower limit. And using the same principle to add this to the mean is 2.78 multiplied by the standard error of the mean gets us to 16. So we know now, once again, that the 95% confidence interval is 8.7 to 16.1. Does it include the mu? Would you reject this null hypothesis or would you accept it? So this time I want an answer.
It's in between the lower limit of 100.
So are we rejecting the null hypothesis or accepting it? Are we accepting this?
No.
Are we accepting the null hypothesis or not?
Yeah.
Why not?
The mean doesn't equal mu.
Well, this is the confidence interval, 2.776. That corresponds, this corresponds to 8. This corresponds to 16.
Okay. Oh, and it's not there.
Mhm.
So
Exactly, we're accepting it because it's in between. So if we have 8 here and 16 here, 11 is right here.
we don't.
So we're accepting the null hypothesis. So that's the idea.
What if it was like 17?
Then it would be outside.
Then it'd be reject.
Then we would reject. That's the idea.
What is in between the limits you accept and hypothesis? Meaning if it's in the bedrock.
Well, those that you accept are actually not within, they're outside, right?
But they're in the.
So as soon as this is outside of the 95% confidence interval,
Then
you're rejecting it.
I mean, then we reject that.
Exactly. Okay. Good. So that's the 95% confidence interval. If we're calculating now a t, and this is So we have the one sample set test that we have done, the set test, the set statistic, is now here replaced by the so-called one sample t-test. I actually didn't mention this particular term to be used for this test. It's a one sample t-test because you're comparing one sample to one reference value. So it's one sample. Because we will in the following, we will do now two sample tests. We're going to do a paired sample t-test, which is next time. And we're going to do an independent sample t-test. The independent sample t-test is a little bit tough to calculate, so that's going to be a longer session. But basically, the one sample t-test is the simplest of all because the calculation is simple. It's the mean, 12.4, minus the mu, divided by the standard error of the mean, which essentially is 1.1. And we know that this is less than our critical t of 2.78, right? Even if we were changing to a one-sided hypothesis, our t would not exceed our critical t. So now lastly, we want to quantify an effect size. And that's essentially done again as mean minus mu divided by the standard deviation rather than the standard error of the mean. As a consequence, we get now effects of 0.47. Is that a small, medium, or large effect size? 0.2 to 0.5, 0.5 to 0.8. It's greater than 0.8 is large. Okay. Any questions? It's considerably simple, right? It's like the only issue usually, and that is really what you need to keep in mind. It's like, why are we doing this exercise? We're doing this exercise because these are not the same distributions. It's not a normal distribution. It follows the shape of a normal distribution, but it's not strictly a normal distribution. To make it look like it's a normal distribution, you're utilizing the degrees of freedom for this modification to get it closer and to resemble the normal distribution. And this is now the important aspect of it. In infinity, with an infinitely large sample size, always 500, your t distribution is actually identical to a set distribution, to a normal distribution. And that's why sample size makes it resemble a normal distribution more. Everything greater than 30, you get away with a normal distribution and set statistic, but generally t statistics are used irrespective of that, of the size. Okay, any questions with any aspect of this? I just want to quickly go back to, and just keep in mind, because just want to make sure that you're visualizing again the aspects of power. Just keep this in mind, that what essentially is statistical rejection. So if you have two samples and you have an alpha, you're basically rejecting this area that exceeds that critical value and is not overlapping with this 5% alpha. So everything that is not overlapping, that's actually your rejection region. That is your probability of not running into a type 2 error where you're not rejecting something, and also not committing a type 1 error. And this can be done by increasing the alpha because it extends that region where these are not overlapping. and you're basically exceeding that critical value. So this is increasing the alphas one way, and this is again, this change to two-tailed to a one-tailed hypothesis. So if you have it on both sides, your critical value is also symmetrically distributed on the distribution, on the normal distribution on both ends. If you are changing to a one-tailed hypothesis, you're having your strength and your power here only on one end, exceeding the critical value, and you have a larger region of statistical power. So just keep this in mind. And also here, same thing, right? If you increase the sample size now, thereby decrease the variability in your sample relatively, and the standard error of the mean is going to be smaller, you're again increasing that region of statistical power. Equally, if you increase the difference and you intensify your intervention, if you ask, for example, your students to sign a contract for 20 sessions rather than 10 sessions, then they may be more likely to come even more often. As an example, likely not going to happen. But so that's the idea, right? So these are the four reasons that lead to an increase in statistical power. Increasing the alpha, changing from a one-tailed to from a two-tailed to a one-tailed hypothesis, increasing the sample size and thereby decreasing the variability and increasing the difference between the sample populations that you're comparing. So this was one sample t-test. Next time on Monday, we're going to start with paired sample t-test. So just to give a little bit of a taste, now we compared one sample to one reference value, which could be a population mean or whatsoever. Next time, we're comparing a sample, following it over time and comparing before to after. All right. Thanks so much. Have a good weekend. See you on Monday. Thank you. Thank you. Thank you. Bye-bye.